Chemistry, we're on to lesson 2 in the reactions unit. This is on chemical equations. So chemical equations are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants combine into new substances called products. So the elements or compounds on the left side of the arrow, those are the elements or reactants that you're starting with, that you want to create a chemical reaction with, but that reaction hasn't happened at that point. So in this case, you're starting with CH4 and oxygen molecules. Over on the right are the products. That's what's going to come out of the chemical reaction. In this case, you have carbon dioxide and water. Many reactions can go backwards, go from right to left, but for right now, we're just going to keep it simple and just talk about reactions always going from left to right, and in most cases, they do. So the one-way arrow indicates that the reaction moves from left to right. So any chemical process that happens in the universe between any elements or compounds can be expressed in one of these simple sentence-like structures called a chemical equation. So here are 3 ways to interpret this equation. The first, we can say that you have one molecule of CH4. CH4 is methane, and you see the 1 out in front as the coefficient. Now, normally you don't write 1s as coefficients in chemistry, but I want you to do it. I want to emphasize that there's a number there. It's not just blank. So when you do have a coefficient of 1, I would like you to write that. So what it's saying is you have one molecule. It's covalently bonded. That's what methane is, CH4. It's 2 nonmetals, covalently bonded, and you have one molecule of that. Now it says to make that reaction happen, you need 2 molecules of oxygen, 2 of the O2 molecules. There they are right there. What you're going to get on the product side is 1 molecule of carbon dioxide and 2 molecules of water. So this is dealing on the molecular level. There could be individual atoms there, but they're not in this particular equation. So you're dealing with individual atoms and molecules in this interpretation of this equation. And it's at first the way we think of what a chemical equation means. Or we can view the equation in terms of moles. That's simply these big baskets of 6.022 times 10 to the 23rd atoms or molecules. And again, why do we want to use these big baskets? Because we can actually physically see them and weigh them on a scale. So that's why we really want to work in moles and think of things as being in terms of moles. So there's the same equation. So now we can think of 1 mole of CH4. That's 6.022 times 10 to the 23rd methane CH4 molecules. It's just a big basket. We just scale everything up so we have enough to be able to see them and weigh them. Then you're also going to need 2 moles of O2. Now notice when you have 2 moles of O2 and 1 mole of CH4 that the molecules are going to match up. You're going to have 1 methane CH4 molecule for every 2 oxygen molecules. It's the same relation as in the last slide, except now we're dealing in big enough numbers to actually be able to see and experience in the real world. And what they're going to do is they're going to combine to produce 1 mole of CO2 and 2 moles of water. So all you've done is taken the molecules in the last slide and multiply them all by 6.022 times 10 to the 23rd, so that we have these large groups of molecules. Finally, the third way is we can view the equations as ratios, and that's really what we should do. So there's the equation. So whatever number of moles of CH4, so you notice what it says below that basket, 1 times however many moles of CH4. It doesn't have to be 1 mole. Reacts with twice as many moles of O2, and what that's going to produce is 1 times some number of moles of CO2 and 2 times whatever number of moles of H2O. So this requires a ratio of 2 moles of oxygen for every 1 mole of CH4, whatever those numbers are. So, in other words, what if instead of 1 mole, we don't always, if this equation was only good if you had exactly 1 mole of CH4 and exactly 2 moles of O2, it wouldn't be a very useful equation. It would be very limited. But if we say that, what if we say, for example, we have 2.5 moles of CH4? Then we need twice that many moles of oxygen. 2 times 2.5 is 5. So if we have 2.5 moles of CH4, we need 5 moles of O2. And then over on the product side, if we had 2.5 moles of CH4, and that's represented by a coefficient of 1, you notice that CO2 is also represented by a coefficient of 1. So that means you're going to get out 2.5 moles of CO2 and 2 times 2.5 or 5 moles of H2O. In other words, you're using those coefficients not as an exact number of moles, but as a multiplier for the number of moles you want. Think about it. What if we wanted 10 moles of CH4? Then you would need 20 moles of oxygen. You'd get out 10 moles of CO2 and 20 moles of H2O. So those coefficients are multipliers for the number of moles that you're going to use. Let's do one more. What about 5 moles of CH4? Then in order to react that, you would need twice that, or 10 moles of O2. That would produce 5 moles of CO2 and 10 moles of H2O. And so that's the way you really want to think of the coefficients, is they're creating a ratio. However many moles of CH4 you want to react, you need twice that many moles of O2. And that's the way we generally should think of the coefficients in a chemical reaction. So we should view the coefficients as ratios of reactants and products. Particulate diagrams provide a simple picture of the motion of atoms in a chemical reaction. The way that chemical compounds break apart and recombine will be covered later in the course. So particulate diagrams show a beginning and final diagram of a reaction. It might also show an intermediate state of the reactants. In other words, when they're in between beginning and final. So that's what we're going to show here. So you see that the CH4 and the O2 broke into individual atoms. Now, how does that happen? It's not just magic. The way it happens is they literally are in an environment in which they can smash into each other hard enough to break apart. So the CH4 is broken into 1 carbon and 4 hydrogen, and the 2 O2s are broken apart into 4 oxygen atoms. And it's just by smashing into each other. Now what they're going to do is they're going to recombine over there on the right. And we will call this a 3-stage particulate diagram. You have your reactants on the left, the intermediate state in the middle, and then over what you see now are the products. 1 carbon dioxide and 2 water molecules, or 1 mole of carbon dioxide, 2 moles of water. Antoine Lavoisier, known as the father of chemistry, developed the idea of conservation of mass in the 1700s. Conservation of mass means that the mass of the reactants before a chemical reaction must equal the mass of the products after the chemical reaction. This means that if you bulldozed and burned Hoover High School to the ground and put a big glass dome over it when you were doing that, the mass of the rubble and smoke would exactly be equal to the mass of the school before it was destroyed. So if you had a billion carbon atoms making up the structure of Hoover High School before you destroyed it, then after you burned it and bulldozed it under that big glass dome that you put over the school, you would have a billion carbon atoms after you destroyed it. You don't increase or decrease the number of atoms. They stay the same. if you had 10 billion oxygen atoms, then you would end up with 10 billion oxygen atoms under that dome somewhere, either in the smoke or in the rubble. You would end up with the same number. And so that's really the way we're going to think of conservation of mass, is you have to have the same number of atoms of each type after the reaction takes place as you had before the reaction takes place. So this means that the number of atoms of each element in the products must equal the number of atoms of each element in the reactants. Alright, and that takes care of this lesson to introduce you to chemical reactions. We're now going to the next few lessons, going to learn how to work with them to determine how much we need and how much we're going to make when we perform a chemical reaction.